I will present the first scientific data application that it is developed in the frame of the DISPEC project. This application concerns the development of improved electron density distribution maps using corrected data from the DISPEC methodologies. The electron density distribution model that we are using is a topside sounder model assisted Digisonde. This model is based on electron density profiles from Alouette and ISIS data, and from each topside profile we extract the scale height and the transition height, and we calculate the ratio. And then, based on the analysis of millions of profiles, we can construct empirical equations of the scale height and transition height, depending on the geomagnetic latitude, day of year, local time, solar flux, and Kp index. The second step is to define the shape of the profile. For this, we are using the alpha Chapman distribution for the oxygen ions and the exponential distribution for the hydrogen ions, which is the dominant species above the transition height, which is the plasma sphere area. The third step is to link the profile to the Digisonde profiler. So based on the data that we get from the Digisonde at the height of the peak density, we modified the Digisonde neutral scale height to comply with the scale height of the topside ionosphere. Finally, the third step is to adjust the electron density profile to the measured GNSS tech parameter at the Digisonde location. And here you can see the equations that we are using for the TAD model, which are on site. This is one-dimensional reconstructed electron density profile at the location of the Digisonde. So we are using the different equations for the plasma sphere, for the top side the ionosphere, and of course for the bottom side ionosphere we rely on the Digisonde extracted profile. This is an example of the profile, and it is obvious that if we integrate the electron density profile up to the level of the peak density or up to the transition height, we can calculate the partial tech for the bottom side ionosphere, for the tech for the top side ionosphere, and for the plasma sphere. This model, the 1D TAD model, has been validated in the past using JUMP and image RPI derived profiles, and the matching is quite reasonable. Now we have to move from the 1D electron density distribution to 3D electron density distribution. For the 1D distribution, the model requires the tech parameter from the GNSS receiver and the electron density profile from the Digisonde station, which is co-located with the GNSS receiver. For the 3D distribution of the electron density, the model requires the map of the tech from GNSS receiver. So if we want to apply this 3D mapping over Europe, we need to get the European tech map, and we need also a European map of the electron density profiles from the Digisonde stations. Now, this second requirement is the most difficult one because we have to consider that although, for instance, in Europe we have more than 100 GNSS receivers, the number of Digisonde stations operating in the area are only 12 in the best case scenario, if all the stations are operating. So it is quite difficult to develop a map with only 12 points. And this is the sequence of steps that we are implementing to derive the 3D electron density model. So we start from the bottom side with a baseline model, which in this case is the Nequick model, and we ingest data from the Digisonde in operation. And in this way, we overcome the problem with the few locations where we have Digisondes in operation, because we update the Nequick grid with the current values from the Digisonde. We also use tech maps, and these tech maps are available through the internet from various sources. In this case, we can often use tech maps from UPC, but there are also other sources. We ingest these maps in the TAD and we apply the empirical equations for the top side and for the plasma sphere. And at the end, we derive the electron density for the whole path, which is bottom side and top side ionosphere. Here you can see some maps that we get with this methodology. And this is the map at 100 kilometer and at 300 kilometer for the same time and day. The 3D electron density distribution maps are validated in this case using swarm in situ data. Here you can see the reference profile from the IRI 2020, and with a red line you can see the Digisonde TAD model, that it is using the Nequick as background, and it is updated with the TAD formulation for the top side. With the green star, you can see the swarm in situ data for this timestamp, which is a daytime ionogram taken on the 9th of June of this year. And on the right hand, you can see another case where again we have a very good matching between swarm data and Digisonde data and TAD data, but in this case also IRI have a good match. Now let's see what DISPEC can offer into this scientific data application. DISPEC can help us to overcome the issue of damaged or incorrect electron density profiles that we could take from the Digisonde stations. In this case, using the sequence that I presented before, we can develop a map for the electron density distribution over Europe. And this is a case for 400 kilometers. For this map, we use data from Tromsø station, from Durb station, from El Arenocillo Digisonde station, and from sopron Digisonde station. And in all these cases, the profiles that we got are scaled correctly using the RT software that it is built in the Digisonde sounders. And having correct scaling, we get also correct reconstructed 3D electron density maps. Here you can see the same map, but in this case, the input files from the Digisonde have some issues. For instance, to reconstruct this map, we use electron density data from Tromsø station again, from Durbu, from Elarinocilio, and from Sopron. However, you can see that the Sopron electron density is wrong. We get wrong scale data from the artist software that runs in the Digisonde, and this may be because of some interferences or some second hop, second reflections of the sporadic layer or from the F2 layer that creates a large uncertainty in the reconstructed electron density model. So in this case, the scaling is incorrect, at least in two locations, Tromsø and Sopron. And so the output of the reconstructed maps present some bubble-like features, which are obviously not correct. Now, in this case, DISPEC can help because we can improve the scaling of the ionograms. Here I present two cases, two ionograms, when both ionograms are recorded in Athens Digisonde, and in both cases artists failed to calculate the correct FOF2 because in the first case the trace, as you can see, is based on the second reflection of the F2 layer. So the scaled FOF2 is 3.5 megahertz, whereas the correct FOF2 is around 4.2 megahertz. And in this case, because of a large gap that interrupted the trace, the artist stopped at the FOF2 equal to 2.28, whereas the FOF2 is equal to 2.6. So the methodology that we are using to rescale the ionograms is based on the concept adopted by human scaler to specify the FOF2 frequency. And the method takes advantage of both O and X wave reflections, and also we consider always that when the O reflection is not very clearly seen in the ionogram, we base our scaling to the X wave reflection, and we use the rule of the half zero frequency to calculate the FOF2. The second step in this methodology is using the clustering methodology for the O trace, and we use the single link hierarchical clustering algorithm. And finally, with the Poland method, we invert the virtual trace to the true height profile. Here you can see the previous example, and I can show how the artist software behaves and how DISPEC software performs. So this is a case where the artist trace stopped before it reaches the FOF2 because of the large gap, whereas DISPEC continues up to the correct value of the FOF2. In this case, where artist started the to identify as a trace the second reflection of the F2 layer and then continues to the first reflection, which has as a result an incorrect calculation of the profile. DISPEC just ignores the second reflection and starts the trace from the lower height below 250 kilometers and then continues correctly up to the FOF2. And here you can see some more elaborated cases. In the top row, you can see an ionogram which records a medium scale TID because we have a fork-like trace here, and it can correctly identify the full trace. In the bottom side of this view graph, you can see again an ionogram which is rather complicated because we have E layer, we have sporadic E layer, we have F1, we have F2, and we have even F3, and the DISPEC manages to correctly identify all the layers. And using the correct data from DISPEC software, we can correctly calculate the maps. And so this is a map which is obviously wrong with bubbles in the middle. And here is a correct electron density map for Europe for the 400 kilometers. So the proposed high-level data products from this SDA1 can be corrected time series for FOF2 and HMF2 characteristics over Digisonde stations. We can also provide 3D electron density distribution grids over the European region for the bottom side ionosphere, and the same grids for the European region for the top side ionosphere. So we are working on these developments, and we hope that within the next months we can provide some mature high-level data products. Thank you very much for your attention.